Okay, so the general solution, we are doing the one-dimensional wave propagation, and it's a change using hydrodynamic relations, then getting into the acoustic wave propagation. We have all the conservation law. Then now we are going to specialize for acoustic wave propagation. Then we are going to use all that relation to solve the shock problem. The reason, only reason is our interest is the phenomena away from, slightly away from, in the vicinity of the charge at the time of explosions. That's the thing, that's the reason. Then for the one-dimensional wave, which is called what wave? I want you to talk. If you don't talk, it's a problem. It's called plane wave. It's a one-dimensional wave. It's like a plane, wave front, acoustic wave front, shock wave front is a plane. Such a plane wave in reality is caused by the nuclear explosion. For the nuclear explosion, of course, at the beginning is a spherical wave. But as it propagates really away, miles away, then it becomes, the wave front is really flat. The curvature is infinite. Then it's a plane wave. In the vicinity of nuclear explosion, I don't have any interest. Of course, the physics part I have and you have interest, but it's going to be all just to wipe out everything on site. Then that's the situation when you say in the vicinity of the nuclear charge. That's the plane wave, away from the spherical wave. Then the wave front curvature is almost flat in reality. So this is called a plane wave. And plane wave, so if this is a wave front, then it contains the pressure, compressive pressure. So so sometimes a shock wave is called the pressure wave. Okay, it carries the pressure, tremendous pressure. So plane wave, the pressure, shock pressure doesn't change as it propagates. So it has a solution for the plane wave equation, one-dimensional wave equation is up there. That's from the 3D, the wave equation. Then, this is the case we are considering only here for the convenience, just to use x-directional wave here. This is a wave front. Then it's moving in that direction. And it has a two-part. That's a wave from the wave equation, 3D wave equation. You can drop the y and z, then just to keep the x directional. And this is as is. This was what? Del square p. Okay. So in the Cartesian coordinate, as we talk, you have this. This is a 1D wave equation. It has a two-part. The first part is what? That's for? Yeah, incident shock wave, like a forward traveling wave. So forward traveling wave is a wave moving positive x direction. And second term is like a reflection wave. or backward traveling wave. I put that name, but it's like a reflection wave. When you have like a rigid wall, when it hit it, then it's gonna return that part. This part is fx minus what I use the notation? T, I'm sorry, this is for time domain, so t minus x c naught, and this is z, reflection wave is a different function, g t plus x over c naught. So that's the two parts in general. Then now we went through Monday. Then I said, okay, let's consider the incident shock wave, which is really forward the traveling wave, which is just the first part of this shock wave pressure. This is a pressure expression. So then I'm going to bring back that equation. What do you call this equation? I said spend an hour after the class, that same day spend the hour. And what do you call these equations? That's a momentum equation, but it has a name in front. Reduced momentum equations, because conservation of momentum equation, we specialize by dropping what term? Dropping the second term in the equation. Okay? Then get down to reduced momentum equation. That's what you have here. Even I put that down 2.3-1 equation. So this is equation to solve with the P is equal to the F function. Then this is 3D, the vector notation for fluid particle velocity. This is a scalar anyway. So now we are dealing with a plane wave. So I'm going to just use the U, and V and W is immaterial because it's one direction. So del U over del T is identical to this. This is del P over del X, right? Y term second and third term drops off. Del P over del X because it's moving in X directions. You could designate this plane wave is moving in Y direction or Z direction, vice versa. But X is common, so that's what I used. So then you can plug in that expression to here. Then you have to be careful here. So you don't have to complete derivations and submit, because I wrote enough for you here. And this is a prime there, F prime. F prime over here is defined like that. But look at this. So up to this is just after you plug in that expression from here, just replace into just x directional components, then del P over del X. Same thing carries over. So F prime is del F, let's say whatever inside, let's call just the parenthesis. F del F parenthesis, okay? Inside is shown already here. Over del X. Then by the chain rule, del F parenthesis over del X is equal to this over del X. Okay? So I'm going to call this term as F prime parenthesis. Clear? Huh? So rewrite this term here. So this term is f prime parenthesis. Then this over del x is 1 minus 1 over C naught, because only that minus 1 over C naught comes right out. Gusto, right? You follow me? When I explain, try to watch. Okay, so this is look like no prime here, but prime is there. So this is identical to shown over here or here. So when you do that, you can just solve that. Just to differentiate, just to integrate, then you can solve that very nicely. So then integrate with respect to time t for this is equal to this part. Then this with respect to dt. So this portion is from integration limit is from t naught to t. So u minus u naught. So over there, u minus u naught is really means is u at time t minus u naught means is u at time t naught. Initial time and final time. Or given time t. Would you close the door, Lee? So this part is u minus u naught. Okay, anyway. So it's 1 over rho naught c naught. So when you integrate this with respect to time t, this prime is over here. Expression is right there. So so when you do that, integrate this part is back to the original f function. So f is p, okay? So it's going to be, this is out, so p minus p naught. So p here is pressure, shock wave pressure at time t, and this is at time t naught. Simply speaking, this equation cast into reality here, this is x direction, positive x direction, and this is a shock wave, plane shock wave front. Before the shock wave front comes, this is u naught and p naught. This is a p, not rho. So before the shock wave, for example, p naught could be just hydrostatic pressure plus atmospheric pressure at the particular location in the water. P naught, before the shock wave hit. And u naught, the fluid particle could have some velocity in the water before the shock wave hit. Okay, it could be 1 feet per second as a tidal wave kind of the thing. Okay, so before, after the shock wave, just behind the shock wave is u and p. You can think in that way. Very easy to solve the problem. So another way of explaining is this. This is the first equation which you must know for the shock problems. So u minus u naught is equal to 1 over rho naught c naught p minus p naught. Very simple, straightforward, but very important relation between shock pressure and also fluid particle velocity. So the wave front, as I wrote, is U naught, P naught, and behind this wave, which is U and P. Think that way. Another way to think is P naught is pressure before the shock wave hit. This could be hydrostatic pressure plus atmospheric pressure, and this P you can think as a P, total P behind the shock wave. So this portion, I can say that this portion you can treat this as a dynamic pressure or gauge pressure. Take away the static component out of total, then it's going to be simply gauge pressure. What that means is when you conduct underwater shock testing, the pressure gauge is like that long and very flimsy to measure the shock pressure. If you put that in the water, then of course there is the cable or cord. Then if you look at the gauge, it registers the pressure as it goes below. Then before the shock testing, I reset this gauge indicating needle to 0. Then after when the shock test you perform, the pressure is dynamic pressure. You eliminate it for the static portion. So that's what you do in the signal processing. If you have a signal, this is a signal, some sort of the signal, this is time t, then you can see the static component, which is like average or mean value, for example, of the pressure. If this is the vertical, the ordinance is pressure, then I can reset this as a 0 right there. Then you can eliminate this part. Then of course you know there's a mean value of pressure right there. That's a static pressure, always the same. You don't have to put that in, carry along when you conduct the dynamic analysis. Okay, that's what you do. You could do it. So now U naught, this is one way of thinking. Okay, U naught, shock compared with the shock wave motion, fluid particle velocity for this is really small compared to this. Then usually you can set this guy equal to 0. Then you can claim that U is equal to 1 over rho C P. Even I drop the rho naught C naught, always that's what we are working on it. So then I can say, okay, from here, the equation, shock solution that you would remember is a simple equation. P is equal to rho C U or rho C V or whatever, okay? That's the relation, very important relation between the plane shock pressure versus fluid particle velocity. When a ship is in neutral buoyancy, you can use U as a ship itself. We'll discuss that later part, maybe a couple of weeks after. This is good for what wave, Chorong? What wave? This is good for what wave? Plane wave. Stupid question. It's a plane wave, okay? But very important equation. For spherical wave, you have additional term, which is called the surge term, as you will see. P is equal to rho Cu or rho Cv. Very important equation. Another way you can think is U minus U naught, whichever. This is the way you think. I suggested this is very nice to understand. Is equal to 1 over rho C U minus 1 over rho C, oh, I'm sorry, rho Cp. Let's wait until I finish the spherical wave, then we'll put it all together, discuss it. So this is just remember this part. Okay, let's remember that. And again, I indicate this at the bottom. This is this, and this this portion. Before I really put this comment, this my lecture note for this particular version is I put all the comments and then I gave you. And this is some other students in the past, some years ago. It wasn't clear, so I just wrote complete derivations. You can just follow this. Complete derivation to get P is equal to rho C. You then explain these parts here. And another, over the years, when I gave a lecture, not only in Naval postgraduate school, many different shipbuilders or research institute, whatever. So now, how can you say that this solution to wave equation, he said, would you substitute back to the wave equations and make sure it has a one-to-one relations? So he kind of suggested, because I think he stuck some point. So that's what I did for him. So I just saved here. This is a solution, general, very general solution. Then I move this term to the right-hand side. Then I just plug into this basic, the plane wave equations. Then you got that. This is identical to this. So del x over del t here, this is wave equations. So this is C naught, then C naught cancels up, so you got the same. So it goes nowhere, it's just same equation. So back to the one-dimensional reduced the wave equation forms. So just some students couldn't see this, so he couldn't get down to the solution what he wanna see. So this is some. I just saved it for some to answer extra questions. Okay. Okay, plane wave. Very simple. So P is equal to what? Rho C U. Remember. As I mentioned, even the shock expert, he claimed, don't see it, but he does all the experimental data reductions and very sophisticated area, but he doesn't know, which is not a good idea. Okay, next wave we're gonna deal with is a spherical wave, mostly for chemical explosion. problem or conventional explosion problem, then you are dealing with the spherical shock wave. So all your work for the underwater explosion simulation problem most of my students are dealing with is a spherical wave. Okay? So because that's the situation that you are dealing with. So spherical wave is somewhat different. The spherical wave was somewhat different. Spherical wave as the shock wave front really propagate, which means radiate. So spherical waves start from the charge, then it generates the shock wave front. Then it keep propagating in what direction? It's called the radial direction. This is radial direction. It propagates into the radial directions. The volume is changing as it propagates. The volume of gaseous product inside the bubble, we talked the bubble, gas bubble, even hold at the time of the explosion, that instantly form the incident shock wave front before the bubble come into picture. Bubble is a pretty late action, and the incident shock wave finishes up within something like a 3 or 4 milliseconds. So we talked before about this is a T and this is a P. As after a certain time, it comes straight down to same as atmospheric pressure plus hydrostatic pressure, that much depth there. So it get down to this. This is incident shock wave pressure. So as it get down to 0, how long is it gonna take? How many milliseconds? Louder. How many milliseconds roughly? 3 or 4, right? Willis is in Singapore Navy. So he has interest on the explosion. So he pay more attention, I can say. 3 or 4 milliseconds. You remember that? Charong, you remember this? I said everything is done in 3 or 4 milliseconds. 3 or 4 milliseconds means 3 over 1,000 milliseconds. Only 3 parts out of 1,000. Everything. So it's much shorter than blinking eyes. Before, blink takes about maybe a second or just less than a second. But shock wave, bang, bang, done. 3 or 4 out of 1,000 seconds. Very extremely fast. So this is I'm drawing here is incident shock wave. Incident like this. This the shock wave front. The shock wave front area is increasing, right? Instantly increases. Energy contained in there is the same for the given size of the charge, but area increases, the shock area. which means as it propagates, the shock pressure contained in the shock wave front is coming down, right? It's reducing. Pressure is force per unit area. So amount of the area is increasing. So naturally, the shock wave, incident shock wave is coming down. This spherical wave, the incident shock wave is keep reducing as it propagates in the radial direction. Remember that. That makes the solution U is equal to 1 over rho C P has one additional term. Pressure, right at the spherical shock wave front, the pressure is coming down, which means the corresponding fluid particle velocity is also coming down. But for the plane wave, same, no change. But spherical wave, the area, wavefront area is large, which means pressure, shock wave pressure is coming down, which means the fluid particle velocity is coming down, then it's changing. That's what the second term is coming up. So this is a shock wave front here. This is like a fluid particle velocity, let's call U. As it increases, this is U1, this is U2. U2 is getting smaller than U1. Of course, the shock wave pressure is P1, this is P2. As time goes by, P2 is coming significantly down. So radial velocity direction is concerned, it's all radial directions, right? There is no fluid particle coming this way. This is axisymmetric situation. Everything is all moving into the radial directions. So all fluid particle velocity magnitude is all same at the given time, right? At the given time. So I said the V over here, V is a vector, is equal to UR times R hat. I'm using the unit vector in radial direction. I call that as R hat, unit vector. It's something like I hat, J hat, or K hat. I use the unit vector in the radial direction as R hat. And UR is a fluid particle velocity in radial direction. That's a magnitude, right? Scalar quantity. And the radial pressure is also function of R. So R is the distance to the shock wave front, spherical shock wave front. I'm not dealing bubble here. It's purely for the incident shock wave. Okay. The momentum equation. Have you seen this equation before, Lee? Have you seen this equation? Have you seen this equation? Yes. This is on page 2.3-1. What do you call this, Willis? What do you call? Reduced momentum equations. Or first order, the wave equations, okay? For the spherical wave. So I put the R, UR, rather than U, because we are dealing with the radial direction only. Then you got that, then you have to solve that. This is page 2.3-2. So you can turn in. You have a copy of my notes, right? So this is equal to 2.3-2. 2.3-2. This relationship. Oh, then you can look at that. You found it. So review after you go back to your office there. So then I don't have to. So this is, you got that, right? This is equal to rho naught times the gradient, scalar product. V is UR, R, right here. Then again differentiate with respect to time t once again. Then this identical, move this guy out, then differentiate with respect to time t. You have to be careful. This UR is a function of time t. Why? UR is changing, right? Reducing magnitude as time goes by, right? This is just a straight algebraic expression, dot, and this rho naught, we put that in, minus we put that in here, the unit vector comes right out, then this is just a different expression after you put the rho naught into the parenthesis. Then from here, this expression, I can change this guy into the P. So now there is one homo, which is due Monday. Don't say I never say that. This is due on Monday. From here to here, you have to look at the del expression in spherical coordinate, which you don't have to derive it yourself, or you can derive if you want to. If you look at the handbook, then you will see that del expression in what coordinate? Spherical coordinate. You will do once in a lifetime. Then get this expression. So this is equal to this. That's what the wave equation for spherical shock wave, okay? You got it? From here, this is equal to this. Then idea is to get the solution. For simple way to get the solution is this R is really independent parameters. Then I can move this guy into inside the differentials, associate with the P. Then it's going to be RP. This is here is RP. And if you look at carefully, this is equal to this. This is really same as 1D wave equation. When you consider the bundle RP, replace that as a P or P prime or P1, then all the solution that you have using the plane wave equation is equally valid if you replace RP by let's say P1. Okay. Then after you got everything, then get back saying that, oh, this P1 is R times P. You follow me? Yeah. So another way to look at the spherical wave, another way, it's always a good idea to look at the same person at front and back. Appearance is all different. To identify a particular person, that's what you do. So here I'm looking in different way for spherical wave. So for the spherical wave, the spherical coordinate is usually identified as r, theta, psi. So r, this is the point, right? This is a point. This is a point, right? So to identify the location in spherical coordinate, you have r, theta is measured from z, and this is a psi. But for the shock wave, spherical shock wave, that's the function of the r only, not the function of the psi or theta, because it's really point symmetric. Then Laplacian in spherical coordinate can be expressed using the 4 term, 1, 2, 3, 4 term. And third and fourth terms involved in theta and psi, for our application, we don't have any symmetric with respect to r, with respect to theta or psi, then you can drop third and fourth term. Right, Sunu? Clear. Then first and second term is what you're going to use for the spherical. We are looking into spherical, the wave produced by the spherical charge. I mentioned to you, even if your charge, when I say charge, is same as explosive, right? Charge is same as explosive. If you have everything I do here, assume the charge shape is spherical. I mentioned to you a couple of times already. What happens if this is a cylindrical shape? You know, you have a big can, then you put all the gunpowder, very sensitive, high explosive mixture in there. Bang! Then you can still consider as a spherical charge. At the time of explosion, instantly, the wave pattern could be different slightly. In material, as it expands, it works like a spherical charge. Okay? So you can do that. So how do you compute? Then you can compute this guy. You have a V cylinder and get the equivalent the volume for sphere. Then you can get the R, right? Jongwon, right? Then you can work out the same way. So when you deal with del square, Laplacian is only 2 terms. Then when you rewrite, R comes right out. You can write these 2 terms combined as a 1. Or you can differentiate, make a partial derivative, then you will end up having these 2 terms because it's R and P are involved. Or you can just rewrite this as I mentioned before, R moved to is independent, the spatial coordinate, independent of course variable of time. then you can put associate with here, which is like this. And RP, if I say RP is P1, you got that equation. Have you seen this equation? Yes, same as, this is same as the plane wave equation. No difference. All I did was replace P by P1. Okay? So then, you know, P1 is RP. Then you know the solution. We have a two-term. But as you look at two-term, as you look at inside, this P1 happen to be R times P. So this P is a spherical wave, spherical shock wave of pressure. So everything is divided by R here. What does it mean? Shock wave of pressure is diminishing, reducing as it propagates, as R distance is growing, right? Because it's divided by R. So you can, I just named it as this is outward wave. The other one is inward wave. If you have a spherical mirror, this is really ball, sphere shape. Inside is all mirror. Reflection is there. Then first term is outgoing wave. Then as it hit the mirror surface, it's going to come straight down, which is inward wave. And all that wave is coming back to the one point, which is at the center. It will come back right at the center. That's the inward wave. Okay? Then all I'm doing next here to solve exactly the same way I did for the plane wave. So now, you know, we have this equation. Then we're going to consider over here only the first part. So here it said, considering the outgoing wave, which means first part, this wave, right? Assuming P is equal to 1 over R and multiplied by the function F. For the plane wave, 1 over R is 1. Why? R is curvature. R is a curvature. Curvature is infinite. Is it 1? It has to be, for plane wave is a 1. And R is really infinite. 1 over infinite is not 1. What's happening here? But anyway, for when the R is really growing, the curvature wave surface is flat. That's what I mean. Okay. So here you plug in this expression, P is equal to first term. That's what I do here. P is equal to this. Then just for algebraic manipulation, and this is a partial differentiate with respect to R. So first you take a derivative for the 1 over R. Next is you take a derivative of F with respect to R. Then there is a trick I use here, F prime. This is F prime. Okay? F prime. So this is F prime here. I want you to finish your derivation. You don't have to submit this. I assigned only one homework today, right? For that spherical wave stuff. And then after this, then you this is equal to that. Then you you integrate. This is integration. Move this guy to this side. Then you integrate then it's UR at time t minus UR at time t naught. Initial time and final time. Initial time and final time. It has a two term. You have two terms here, one term and second term. And second term is really identical. This is 1 over rho naught C naught. This guy is P minus P naught. Very same. But you have one additional term here. One additional term, which is called the surge term. This is caused by change in velocity, fluid particle velocity. Okay? Then if you want to rewrite, then simple rewrite. This second term put in a first, and this guy is in second. This is sometimes called the surge term. Some people call it after flow term, but just a name. But this is caused by the variation of the shock wave pressure between T naught to T. Okay? So you can think of this as like give a thought on the plane wave. U and P is behind the spherical wave, and U naught, P naught is in front of the spherical wave. You can think. But remember, this second term sometimes affect 10%, even higher. Okay. So I'll give a little bit more talk, few more minutes after we come back on Friday, then we'll continue. Okay?